So with the example of Gambler's ruin problem in mind, let us try to set up the notation in the general case. So in the general case, of course, we will need the canonical decomposition, but the state space is expressed as the union of T and C1, C2, and so on, where T is the set of all transient states. And this is not necessarily one communication class, as was the case in the Gambler's ruin problem. It was just one communication class, but it can be union of a bunch of transient classes in general. And each CI is a closed and recurrent class. Now what we want is, we want to compute, our interest is this time. The first time, this is the first time the Markov chain hits T complement. So this means this is the exit time of T. This would be the time that we'll be interested in. And of course, in the Gambler's ruin problem, this T was finite with probability 1. Starting from A, tau was finite with probability 1. Okay, the T complement just means two states, 0 or A plus B, and this was finite with probability 1. In general, there is no reason why this should be the case. So therefore, we'll actually make an assumption that starting from any state I, tau is finite with probability 1. And as we will see later, this is the case if the state space is finite, for example. So Gambler's ruin problem is an example. The state space was finite. But in general, for any Markov chain where state space is finite, this assumption will hold. By the way, this assumption, even though I'm writing it for all I in S, but if I is already in T complement, then obviously this tau is 0. And therefore, this is a trivial statement. So actually, the assumption is done for all the i's which are in T. So essentially what it says, the assumption says, is that starting from any transient state, will eventually hit a recurrent state with probability 1. Now this may not happen when the state space is infinite. Okay, there can be many examples can be given, but one example would be, say, all states are transient. Then of course, you will never be able to hit any recurrent state at all. Anyway, so under the above assumption, therefore, x tau is the first state that is hit outside. Remember that the Markov chain may not stop at x tau. In the Gambler's ruin case, that was the case because T complement consists of two states which are both absorbing. In general, recurrent states may not all be absorbing, right? So therefore, the Markov chain may not stop. So this is not the final value of the Markov chain or anything. This is just x tau is just the first state that is hit outside T. So that means x tau is the first recurrent state that the Markov chain reaches. Okay, so we have the canonical decomposition and we have the exit time, which we assume to be finite with probability 1 starting from any state. And this will be the case when the state space is finite. And then we are going to define for every transient state T, I in T, and every recurrent state K, will define uik to be the probability that the Markov chain starting from I exits T because hitting the state K, hitting the recurrent state K. So this is the probability that starting from I, x tau is equal to K. This is the probability that the chain exits T because of hitting the state K. So this means first time it exits T, it hits the state K. That's what this means. So this is the quantity that we have defined. As I said, we'll denote it by uik. This is the probability starting from I, the chain, exits T because of hitting the state key. Now note that if K is actually an absorbing state, as was the case in the gambler's ruin problem, uik is actually the probability that the chain starting from I gets absorbed in K. Okay. On the other hand, more generally, it may not be an absorbing state, but the chain starting from I gets absorbed. Even if there is no absorbing state, all the recurrent classes are actually closed. So therefore, once you reach one of the recurrent class, the Markov chain actually is trapped in that recurrent class. So the Markov chain gets absorbed in that class. What is the chance that the Markov chain gets absorbed in this closed recurrent class CLC? This will happen with probability. We'll denote it by UICL, which is essentially the probability that X tau is in CL. Starting from I, X tau is in CL. So this can be computed from all these UIKs by taking a sum over K belonging to CL. So therefore, the UIKs, when K is an absorbing state, gives you an absorption probability, getting the Markov chain getting absorbed in the state K. On the other hand, even if it is not, even if it, it is not K is not an absorbing state, it actually has information about getting absorbed in a particular closed recurrent class. By using this, we'll get the probability of the Markov chain getting absorbed in the closed recurrent class CL. So this is why we'll abuse the terminology and we'll call UIKs as absorbing probabilities. Absorption probabilities, sorry. So absorption may not mean getting absorbed in a particular state. If it is indeed an absorbing state, yes, but otherwise this would mean getting absorbed in a particular closed class. So this has information about probabilities of getting absorbed in a class. And that's what we are going to, why you are interested in these quantities. So how are we going to compute these things? So what we will do is we are going to partition this transition matrix P as this, where this Q is essentially the restriction of P to the transient states. So this means Qij is just Pij, I and j running over T. That's all. On the other hand, this matrix R is essentially, these are the transitions from transient states to recurrent states. So these are the probabilities, first order transition probabilities PKL. K is a transient state, L is a recurrent state. Now what is P2 here, by the way? I didn't mention it, but P2 is basically the transition matrix P restricted to the recurrent states. And we know that the recurrent states, if you look at the set of all recurrent states, that's a closed set. Because from a recurrent state, you will actually never go to a transient state. You're always, from a recurrent state, wherever you go, that's also going to be recurrent. So therefore, these probabilities are zero. This is the probability of transition from a recurrent state to a transient state. So that is zero. And these are the probabilities these are the transitions between the recurrent states. Of course, this will be further, this will look like a block diagonal matrix. It will be further broken up into blocks, which I'm not writing in details here. The reason I'm not writing is that this probability, this matrix P2 will have no role to play in computation of these absorption probabilities. Now remember that this is just an intuitive statement now, but this is a heuristic kind of statement now, but we'll actually write it precisely, and then you will see this is the case. Now, what is UIK? UIK is about starting from I, and I is a transient state. Starting from a transient state, you hit a recurrence state for the first time at k. So that means starting from I, you will always stay within the transient states. And finally, you will hit k as your first recurrent state. So therefore, how the transition is happening in between the recurrent states, that is not going to play any role in the computation of this probability, because this probability is always about, this probability can be computed from just the matrices Q and R, because it's always how a transition happens between the transient states, and finally how it happens from one transient state to K. Okay? And before this K, there is no other recurrent state that is being hit. So therefore, there is this part P2 is completely going to be redundant for this calculation. Okay, so we'll also see it more precisely when we see the form of the absorption probability, CYK.